Good morning. Let us start the tutorial number 5. It's on Exergy balance. First, we will take a few problems in systems, then we go to control volumes. Problem number 5. An iron block specific heat is given as 444 joule per kg Kelvin at 85 degrees centigrade is kept in an insulated tank that contains 0.1 meter cube of water. Specific heat is 4180 joule per kg Kelvin. The water's initial temperature is 20 degrees centigrade. Simultaneously, a paddle wheel within the tank rotates to stir the water. The paddle wheel is driven by a motor supplying a power of 200 watts. After 20 minutes, the system attains thermal equilibrium with a final temperature of 24 degrees centigrade. Surroundings is at 20 degrees centigrade. Determine the mass of the iron block, the exergy destroyed during this process. So, the insulated tank has some water at 20 degrees and the iron block, which is hotter than that, 85 degrees, is placed inside that. And the stirrer works on the water so that the equilibrium, thermal equilibrium is attained after a certain amount of time. So, solution. The block's initial temperature is 85 degrees centigrade, then water's temperature is 20 degrees centigrade, then the final temperature for both is 24 degrees centigrade and the ambient temperature is 20 degrees centigrade, and the volume is 0.1 meter cube, and the specific heats are given. For the block it is 444 joule per kg Kelvin, and for the water it is 4180 joule per kg Kelvin. So, for the iron block, first law is applied, Q minus W equal to delta U, where it's insulated. So, the system is iron block plus water tank. So, both together insulated. So, Q equal to 0. So, minus W equal to delta U. So, now W paddle, that is stirrer work, that is 200 joules per second, that is 200 watts power. So, that into 20 minutes into 60 second per minute. So, that will be equal to 24 240,000 joules. But here one assumption is made, whatever motor supplies to the paddle wheel, it just takes it, there is no loss. So, we will say assuming no loss between motor and shaft that rotates the paddle wheel. What is mass of water? Equal to volume into density of water. So, density of water can be taken as 1000 kilogram per meter cube. Volume is in meter cube, which is given in the problem. So, the mass comes out to be 100 kg. So, from the first law I can write minus Q minus W. So, minus of minus 240,000 joules. So, please understand this minus sign comes because work is done on the system, okay, equal to, say, MB be the mass of the block into C into delta T is 24 minus 85, and for water MW is 100 into its C is 4180 into 24 minus 20. So that will imply the mass of the block is 52.87 kg. That is the first part of the problem. Second part, entropy balance, that is the entropy generation Sgen will be equal to the entropy change for the block plus entropy change for the water. Okay, now we know the mass, so I will say M block C block into ln of T final by T block initial plus M water C water into ln of T final by T water initial. Now you can see that this temperature has to be in Kelvin here. So 52.87, which we have calculated, into C is 444 into ln of T final is 24 plus 273. So 297 divided by initial temperature 85. So 85 plus 273 plus this 100 into 4180 into ln of T final is 297 divided by initial temperature of water was 20. So 293. So this will be equal to 1282.87 joule per Kelvin. That is the entropy generation. So Exergy destroyed equal to T naught into Sgen, which is equal to T naught is given as ambient temperature is given as 20. So 273 plus 20 times 1282.87, which is equal to 382,294.7 joules or 382.3 kilojoules. So that is the Exergy destroyed. So then the sixth problem, a frictionless leak-proof piston cylinder device contains a mixture of gases with mole fractions of 0.25 for neon, 0.5 for oxygen and 0.25 for nitrogen. The diameter of the piston is 25.25 centimeter. The initial volume enclosed by the piston cylinder is 0.1 meter cube and the initial temperature is 10 degrees centigrade. The initial pressure is 200 kilopascal. So this is the condition. It's a mixture of ideal gases. Now heat added slowly and the piston moves by distance of 50 centimeter. Please understand that frictionless piston is there, so that the piston moves up by a distance of 50 centimeter due to slow heat addition. The molecular weights of neon, oxygen and nitrogen are given as 20, 32 and 28 respectively, and the specified constant volume Cv for neon, oxygen and nitrogen are 618, 658 and 743 joule per kg Kelvin respectively. Ambient pressure is 100 kilopascals and the temperature is 10 degrees centigrade, which is the initial temperature. Calculate the work and heat interaction and the Exergy change. So it's a ideal gas mixture. So here first we will find the molecular weight of the mixture, which is equal to sigma I equal to 1 to n xi molecular weight of I. So here it will be equal to 0.25 mole fraction of neon into molecular weight of neon, that is 20 plus 0.5 into 32 plus 0.25 into 28, which turns out to be 28 kilogram per kilomole. Now I can calculate the specific gas constant of the mixture R mix equal to the universal gas constant divided by the molecular weight of the mixture, which is equal to 8314 joule per kilomole Kelvin divided by 28 kilogram per kilomole. So which is equal to 297 joule per kg Kelvin, the specific gas constant of the mixture. So let us see that the specific heat Cv is given in joule per kg Kelvin. So to find the Cv mix can be found as sigma I equal to 1 to n mass fraction of this component divided by multiplied by the specific heat at constant volume of the component. So this has to be summed up. For here the n number of component is 3. So we have to find the mass fractions. So mass fraction of neon can be found as the mole fraction of neon into molecular weight of neon divided by molecular weight of the mixture. Okay, we know the mole fraction, which is equal to 0.25 into 20 divided by 28. So that will be equal to 0.179. Similarly, I can find molecular weight of say mass fraction of O2 as 0.571 and that of nitrogen as 0.25. Okay, so now mass fractions are got, so that we can get Cv mix be equal to, applying I equal to 1 to 3 Yi Cvi, I get Cv mix as 672.1 joule per kg Kelvin. Okay, so you would understand that the mass fraction is used because Cv is given on per kg basis. Now, what is work done during the process? So basically you can see that the process is a constant pressure process. Because the piston is free to move and it actually moves as the heat is applied. There is no increase or decrease in the pressure as it moves out. So it's a constant pressure process. So that means displacement work will be equal to integral P dV equal to P into delta V, which is equal to P is nothing but 200 kilopascals. So basically please see that the pressure remains constant at 200 kilopascals. This is due to atmospheric pressure of 100 kilopascals plus the piston has some weight. So that actually imparts to 100 kilopascals more. So total is 200 kilopascals. So that is written as 10 power 3. And what is delta V? Delta V is nothing but A, area of cross section of piston, into delta H, that is height moved by the piston. So area of piston is nothing but pi by 4 diameter of piston square. So diameter of piston is given as 25, so which is equal to pi by 4 into 25.25 into 10 power minus 2, that is converting centimeters to meters. So that is this. Then delta H is piston moves up by 50 centimeters, which is equal to 50 into 10 power minus 2 meters. So substituting that, I will get W as 5007 joules, that is W. Now change in internal energy delta U will be equal to mass of the system into CV mix into T2 minus T1. So, I have to find mass and I have to find T2. T1 is known, CV mix is known, so I have to find these two. So, how to find mass? Mass of the system can be found by using the equation of state, that is P V V by RT. Here R mix into T. So, here this will be equal to 200 into 10 power 3 into volume. Volume is given as 0.1 in the problem. So, go back and see 0.1 initial volume is 0.1 meter cube divided by the initial temperature is 10 degrees. So, this divided by R mix is calculated as 297 into 10 degrees, so 273 plus 10. So, that will give the mass as 0.238 kg. So, then T2, how will you find T2? T2 can be found as, again from the equation of state, P2V2 divided by mass of the mixture into R of the mixture. Okay, so that is equal to, pressure remains constant. So, initial pressure is equal to final pressure, that is 200 kilopascals into, what is the volume? Volume is basically V2 will be equal to V1 plus delta V. So, V1 is 0.1 plus delta V is the area into delta H divided by mass is 0.238 that we have calculated, mass of the mixture, into R is 297. So, when you substitute these values, I get T2 as 353.7 Kelvin. So, that is the, so now I know these values, I can calculate delta U. Delta U comes out as 11309.2 joules. So, apply first law, Q minus W equal to delta U. I know the value of W, I know the value of delta U. So, I can find Q equal to 5007 plus 11309.2, which will be equal to 16316 joules or 16.316 kilojoules. So, now change in specific entropy, that is S2 minus S1. Let us calculate that. That will be equal to Cp mix ln T2 by T1 minus R mix ln P2 by P1, but P2 and P1 are the same, so this will be 0. What is Cp mix? So, Cp mix equal to R mix plus Cv mix. So, that will be 297 plus 672.1, which we have calculated. So, that we can substitute here. So, S2 minus S1 will be equal to 216.11 joule per kg Kelvin. That will be the change in entropy. So, why I need change in entropy? Because I want to calculate change in specific exergy, which is equal to Phi2 minus Phi1, which can be written as U2 minus U1 plus P0 times V2 minus V1 minus T0 times S2 minus S1. change in the exergy between the final and initial states. Okay, now this can be written as V2 minus V1 can be written U2 minus U1 is nothing but CV mix into T2 minus T1 plus P naught is 100 kilopascals. So that this into 10 power 3 into V2, V2 minus V1, that is V2 by M minus V1 by M minus T naught. T naught is given as 10 degrees centigrade. So that is 283 into S2 minus S1, which we have calculated. So substituting the values, I get Exergy change as 28367.34 joules. So that is the, so you can see that due to the heat, basically heat is added, so that the Exergy has increased from state 1 to state 2. So this is about this problem. So again, this is a system level problem where in a piston cylinder device, a mixture of gases is heated from initial temperature of 10 degrees to final temperature, which is calculated as 353.7 Kelvin, and due to which the exergy has increased. Some positive work output of 5007 joules have also come out. So now we will go to exergy balance for control volumes. Here, the seventh problem, air is compressed steadily from 100 kilopascals and 17 degrees, so initial entry state, to 600 kilopascals and 167 degrees centigrade. You can see the increase in pressure and temperature due to the compression at a rate of 2.1 kilogram per minute. Okay, so this is the flow rate of the air. It's a steady flow. The power input for the compressor is 8 kilowatt. That has been supplied from the surroundings to the compressor. Neglecting the changes in the kinetic and potential energies, determine the second law efficiency of the compressor, and the surrounding temperature is given as the initial state temperature of 17 degrees centigrade. So this is the problem solution. First law can be written as Q dot minus W dot equal to M dot into H2 minus H1. The kinetic energy potential changes are neglected. Okay, now Q dot is not known. It is not given that the compression process is adiabatic. Okay, so that means we cannot just neglect Q dot here. But power of the power input is given 8 kilowatts. So we can substitute that Q dot minus 8 kilowatts, that is 8000 watts. So it's a power input. So I put a negative sign here, equal to M dot. M dot is given as 2.1 by 60, that is 2.1 kilogram per minute. So I have converted into kg per second into Cp. Cp we can take as 1005, that is Cp into T2 minus T1. So that is, this is 440 Kelvin and this is 290 Kelvin. So substitute everything, I get Q dot straight away. So you can see that Q dot comes out as minus 2723.75 watts. The rate at which heat is rejected from the compressor, that is given here. There is a heat loss. Now, second one is second law efficiency you have to get. So, second law efficiency, to get the second law efficiency, I have to find the actual work and the work actual which is given, but we have to find the either irreversibility or the exergy change. So, let us say rate of change in exergy, so which is written as Z2 minus Z. 1, the word dot indicates that is rate. So, that is given as m dot into h2 minus h1 minus t naught into delta s over a dot, that is the rate of change of entropy. So, between the inlet which is assigned a number of 1 and exit which is assigned a number of 2. So, now we will find delta S first. Delta S equal to 2.1 by 60, that is the mass flow rate, into Cp into ln T2 440 divided by T1, that is 290, minus R is 287 into ln of 600, which is the final pressure, 600 kilopascals, divided by 100, which is the initial pressure. So, that is the delta S. So, you can calculate delta S as minus 3.33 watt per Kelvin. So, now we can get the change in the rate of exergy, which is equal to mass flow rate into Cp into delta T. Delta T is 440, final temperature minus initial temperature, that is H2 minus H1 minus T naught. T naught is minus 290 into, this is 3.33 which we have calculated, that is delta S. This is T naught and this is delta S over a dot. So, that you get the value as 6241.95 watts. So, this change in the rate of exergy represents the reversible work, output of input, reversible which is given as input to the work given as input to the compressor. So, second law efficiency of a work absorbing device like compressor will be reversible work divided by the actual work, which is equal to 6241.95 divided by the actual work is given in the problem as 8000. So, that will be equal to 0.78 or 78%. So, you can see that in this problem the second law efficiency is asked. For a work absorbing device, the reversible work input divided by the actual work input, because the actual work input will be higher for a work absorbing device, and because of the irreversibility, but the reversible work input will be lower than, that is the reversible work without any irreversibility, whatever work you supply to achieve the same compression between 100 kilopascals to 600 kilopascals, that is actually given as reversible work input, but actual work input includes the irreversibility also. Obviously, you can see that the ratio of that is less than 1, that is 78%. You can see that the change in entropy here is negative. However, if you calculate the S gen, that is nothing but delta S minus Q dot by T naught. If you do that, that will be positive. Okay, so Even you can do like that. So, if you calculate basically the delta S minus Q dot by T naught, that will be delta S gen, that multiplied by T naught will give you the Exergy destroyed. So, when you subtract from this actual the Exergy destroyed, you will get the reversible work. That is another way to do. Basically, that is what we are doing here. So, this is the, anyway, the Q is also have to be added here. That is, since it is happening to the ambient, we are not added in the Exergy part.